Let's try another example. So in this one, we have a particle that's moving along a straight line, and we know its velocity function. So the velocity at time t is given by this function right here, v of t equal to t squared minus t minus 6. And our units are meters per second. All right, so for the first part, we want to find the displacement of this particle during the time interval from 1 to 4. All right, so how do we do this? Well, we want to find, let's write it out. We want to find the displacement during that time interval from 1 to 4. All right, so we know the velocity. So there's different ways to find velocity or displacement based on what function you have. So if we had our position function, well, the way to figure out displacement is you would just take the ending position and the starting position and calculate their difference. But we only have the velocity function here. So what we're going to do to find this displacement, we're actually going to integrate our velocity function. And we're going to integrate over this time interval from 1 to 4. So we're going to calculate this definite integral. That's going to give us displacement. All right, so let's fill in our function. So we're doing the integral from 1 to 4. Our function here is t squared minus t minus 6. And we're integrating with respect to time, t. All right, so let's get the antiderivative. This is just a regular definite integral now. So get the antiderivative. It's 1/3 t cubed minus 1/2 t squared minus 6t. And then we're going to evaluate from t equals 1 to t equals 4. All right, so we have our antiderivative. Let's plug in. Top number is going to go in first. Bottom number is going to go in second. And then we subtract. So it helps kind of write out the framework for these, especially with big antiderivatives like this. It helps to kind of write out the framework here. So let's take 4, plug it in. What do we get? 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4. And I need a little bit more space there. There we go. All right, so that's what we get when we plug the top number in. Then we're going to plug 1 in, plug the bottom number into our antiderivative. And sometimes it's helpful when you're plugging things in, try to simplify just a little bit as you go. So if we're plugging 1 in, well, 1 cubed is 1. Powers of 1 are 1. And we don't normally write multiplication by 1. So when I plug 1 into this first piece, you could write 1 cubed, but most likely you're just going to write this as just 1/3. Same thing over here. We could write 1/2 times 1 squared, but we don't normally, you can do the 1 squared in your head. So we would just probably write this as 1/3 minus 1/2 minus 6. Same thing with over here, the 6 times 4. Probably just do that as 24. All right. Well, in any case, this is what we get. And we can do the arithmetic here, and we end up with -9/2 as our answer. Well, as the value of this definite integral. Not quite our answer yet. So when we talk about displacement, and we're given units, so we're given units, meters per second, well, we want to include a unit for our displacement. And we can see, based on this, we're measuring our position, our distance, using meters. So this is going to be -9/2 meters is our units. That's the first thing to note. The second thing, when we look at this, there's kind of 2 components to this. There's this negative right here, and then there's this number. And what we're seeing here, the way to kind of read what this value says, or what we're doing with displacement, is we have this time interval that we're interested in from 1 to 4. And what we're doing is we have a very specific starting place and a very specific ending place. Starting position and ending position. And what this displacement is saying is our particle might have been moving all over the place. But what this displacement captures is just, well, where is your ending position relative to that starting position? So what this is telling me is that relative to our starting place, our ending location is 9.5 meters in the negative direction. So this negative here is really telling us we've gone in the negative direction. So we ended up, wherever we started, we ended up 9.5 meters to the left of our, or in the negative direction of our starting location. So normally negative if is left or down. It doesn't have to be. The direction could be, you could specify any directions here. But the value that we're getting here is telling us that when we started moving and where we ended moving, from time equals 1 to time equals 4 here, our ending location was 9.5 meters in the negative direction relative to our starting place. All right, so when we do this, it's helpful to just remember displacement can be negative. There's a direction component to displacement. All right, now we're going to contrast that with total distance. And that's what we'll look at next, is the total distance traveled by our particle during this same time interval from 1 to 4. All right, so in this case, what we're going to see, worth mentioning, total distance can only be, well, can't be negative. So when we talk about total distance traveled, what we're trying to do essentially is kind of strip out the direction component from our calculations, and we just want to know how much ground do we actually cover. You know, we might be retracing some of our steps, but we want to figure out how much ground did we cover. So total distance cannot be negative. It can only be positive, or in the trivial case, if our object's not moving, well then total distance could be 0. But total distance can't be negative. All right, so how do we calculate total distance if we have the velocity function? Well, it turns out it's also an integration, but it's going to be more involved. So the integration we're going to do is from 1 to 4 of our absolute value of our velocity. And this absolute value really complicates things. We can't just ignore it, because absolute value doesn't really have a nice antiderivative. The way we're going to work with this is we kind of have to split up our integration. And how we're going to do it is we're going to figure out the distance that we travel in the positive direction. We're going to split up this calculation. And we're going to do 2 separate calculations. We're going to first figure out the distance that we travel going in the positive direction. Then we'll figure out the distance that we travel going in the negative direction. And so these will be 2 different distances that we get. And to get the total distance, we add these results together. All right. So we're going to split this integral up. And how we split this integral up is based on where the function, in this case the velocity function, is 0. So we're going to do a little bit of work off to the side here. First, we're going to figure out where our velocity is 0. And why that's important is because then we're going to do a sign chart for our function. So we're really interested in knowing, when are we moving in the positive direction? When are we moving in the negative direction? And so that's the information we're going to get from this sign chart. The sign chart for our velocity is going to tell us the intervals of time when we're moving in the positive direction versus the interval of time where we're moving in the negative direction. So we're going to do these 2 things, and that's going to tell us when we're actually going in the positive and when we're actually going in the negative direction. All right, so first let's figure out when our velocity is 0. And to help with that, we're going to factor our function. So it turns out this does factor very nicely into t minus 3 times t plus 2. So we're just going to use that factored version here. So we set our factored version equal to 0. And then each of these factors we can solve. So we get t is equal to 3 and t is equal to negative 2. All right, so it looks like there's two places or two times when our velocity is 0. All right, so now we're going to do our sign chart for our function, and we're only going to worry about this interval from 1 to 4. So we're going to plot that time interval from 1 to 4. And we're only going to use, on this time interval, we're only going to use these time values where our velocity is 0 that actually occur inside the interval. So in this case, t equals 3 is the only one we're going to use because that actually occurs inside this interval that we're interested in. So we're also going to plot that. So at time 3, we are interested in time 3. And so what we're going to do is we're going to figure out the sign of our velocity function on each of these smaller intervals, this interval from 1 to 3, and then the interval from 3 to 4. And so why we're interested in this time 3 is because that's where our velocity function is 0. And that's the only way a function can switch from being positive to negative, is if it goes through that place in the middle, which is 0. So 0 is kind of the middle ground between the positive values and the negative values. So the only way you can switch direction here for a continuous function is if you, some point in the middle, you're 0. All right, so let's do our sign chart for velocity. And to help, let's use these factors. Not necessary, but it can be helpful. So let's write down our factors here, t minus 3 and t plus 2. And then we can do a sign chart, or we could use test numbers if needed. So for this first interval, from 1 to 3, I might use a test number 2. Plug 2 into each of these factors. When I plug it into this first factor, I end up with a negative. And then into that second factor, I get a positive. So a negative times a positive is negative. And then from 3 to 4, pick a test number inside that. So maybe like 3.5. And then plug it into each of these factors. 3.5 into here, I get 3.5 minus 3, which is positive. And then 3.5 in down here is positive 5.5, so another positive. And so positive times positive gives me positive. All right, so what we're seeing here is on this interval from 3 to 4, our result is our velocity function is positive. So what that means is on this time interval from 3 to 4, we're traveling in the positive direction. So if we wanted to calculate the distance in the positive direction here, the way we would do it is we're going to integrate over that time interval from 3 to 4. So we know we're traveling in that positive direction from 3 to 4, so that's what we're going to integrate from 3 to 4. Now we also know that the velocity is positive on this time interval. So the absolute value, if our velocity function is positive, the absolute value function, or the absolute value sign, doesn't do anything. So this calculation on this interval from 3 to 4, we're just going to integrate just our regular old velocity function. So we can, the absolute value doesn't really do anything. So we can just drop it. All right, so let's do that calculation. So we're going to use our velocity function here, which is t squared minus t minus 6. And what do we get? We won't go through the details here. Very similar to what we did for the integration and displacement there. But what we get here is 17 over 6. And since we're doing a distance here, make sure we include our units, which in this case is meters. So during this time interval from 3 to 4, we're slowly moving in the positive direction. And so the distance that we travel in that positive direction, we can calculate with this definite integral from 3 to 4, and we get 17/6 meters. All right, so now where things get a little bit more involved, not too bad, but where when we want to calculate the distance that we travel going in the negative direction. So we go to our sign chart, and we see that from 1 to 3, that's where our velocity is negative. So on this interval from 1 to 3, we're traveling in the negative direction. So to get the distance, we're going to integrate from 1 to 3. Now, the difference here is from 1 to 3, our velocity function is negative. So what does this absolute value sign do if the quantity inside is negative? Well, the way absolute value works is it kind of works like a double negative. So we're going to have our velocity function, but then we're going to make an adjustment for the fact that velocity is negative from 1 to 3. So this absolute value sign, this negative in front, is really just negating this velocity value in here. That's negative. Our velocity function is negative. So the absolute value sign kind of does a double negative in order to get all those negatives to cancel. So this is the one adjustment that we have to make for our distance calculation, is that when we're traveling in the negative direction, we're still going to integrate over the time interval there where we are traveling in that negative direction. We're still going to integrate our velocity function, but now the fact that we're traveling in the negative direction means we need to make this negative, sort of like a double negative. All right, so let's see what we would get. And so we would set up our integration just like this. So this would be the negative of the integral from 1 to 3 of t squared minus t minus 6. And if we just were to do this definite integral, what we would get is, what do we get? Negative 22/3. So we don't want distance to be negative. So what this adjustment is really doing is it's giving us a double negative here. So if we were just going to do this definite integral, the definite integral by itself without that adjustment negative in front would have been negative 22/3. That's no good for a distance. So essentially what we've done is this, by traveling in this negative direction, the way we adjust for that is with a double negative. And so we end up with 22/3, and the units here are meters. So the distance that we travel in the positive direction we found was 17/6 meters. The distance that we travel in the negative direction we found was 22/3 meters. And we just need to put it all together. So the total distance that we travel from 1 to 4 is just the sum of those two distances we found. So 17/6 meters plus 22/3 meters, which ends up being 61/6 meters. And so there's our total distance. And just note, it's positive. So you shouldn't get a negative here. So distance should be positive. All right. Well, let's just go back and check our displacement. So we have these two gadgets that we found, the distance in the positive direction and distance in the negative direction. Normally we wouldn't calculate displacement like this, but another way to think of displacement is we can think of this as distance in the positive direction the distance in the negative direction, and instead of adding these two values like we do for total distance, we subtract. So it's the difference of these two distances. Excuse me. So what did we find for the distance in the positive direction? We found it was 17 over 6 meters. What did we find for the distance in the negative direction? We found that it was 22 over 3 meters, and we subtract. And if you were to do this, get a common denominator, do the arithmetic, you would end up with negative 9/2, just like we found just doing the definite integral. So it's just maybe another way to think of it for displacement. It's the distance in the positive direction minus the distance in the negative direction. Normally we wouldn't necessarily do it this way. We would just kind of do this definite integral, but it checks out. All right, so let's look at this adjustment. Where is this negative coming from? And it's really coming from this absolute value sign. So let's just look at this a little bit further. And that's what we're going to do in part C, is why do we actually need to split up the integral when we're integrating the absolute value of our function? And the reason has to do with the fact that the absolute value function is a piecewise function. So if we were to look at the absolute value of the velocity function, this is actually defined piecewise based on where our velocity is positive and where is it negative. So if our velocity is positive or 0, the way this absolute value function works doesn't do anything. It just gives you out the velocity function. So this is sort of like the output if this condition is met. Well, what happens if the velocity is negative? What happens if this term inside the absolute value sign is negative? Well, what the absolute value sign does is it, in some way, it does a double negative. So if your velocity, if v of t is negative, well then to make it positive, you just multiply by a negative. You do a double negative. So if v of t, if this velocity is negative, well, that's negative. We have this other negative here. That's two negatives. The result here is going to be positive. So that's what the absolute value function is really doing, is it's kind of behind the scenes. It's behaving like this piecewise function. And so piecewise functions are difficult to integrate because, well, they behave, there's different formulas here to use based on these conditions. And so what we found, we did a little sign chart before, and we did our interval from 1 to 4. And then we had this place in the middle at 3. And what we did is we looked at the velocity. We looked at our velocity function and we figured out, well, where is it negative and where is it positive? So we found that it was negative on this interval from 1 to 3. We found that it was positive on this interval from 3 to 4. And then right at 3, we figured out it was 0. So if we were going to investigate this definition a little bit further, we can actually say more exactly what these inequalities would be. So we know our velocity function is greater than or equal to 0 on this interval from 3 to 4. So we could say the absolute value of v of t is just v of t on that interval from 3 to 4. And then we also know where, we're interested, well, where is this function less than 0? Where is it negative? Well, we found that on our sign chart as well. So if the velocity, or if if we're in this interval from 1 to 3, so if t is greater than or equal to 1 but less than 3, so if we're in that interval, well, velocity is negative. So the way we adjust for that negative velocity, the way the absolute value sign works, is it makes it a double negative. So when we were going to do our total distance calculation during this interval from 1 to 4, that's just the integral from 1 to 4 of the absolute value of velocity. And so we have this function we're integrating, absolute value of velocity here, really is this piecewise function. And so the way we do the definite integral for a piecewise function, and we've done one similar to this before, is we have to split up our integration based on where these different pieces split up. So we see that our piecewise function here splits up at 3. So if we were going to do this, we would integrate from 1 to 3. And then separately, we would integrate from 3 to 4. And this is the way you handle a piecewise function. You have to split up the integration based on where those pieces split up. Well, now, once we have these integrals all split up, then we can actually start using these single formulas here. So on this interval from 1 to 3, our absolute value function is really this. And we could put the negative in front. So this first integral, if we use this definition, becomes the negative of the integral from 1 to 3 of our velocity function. And then if we look on the interval from 3 to 4, well, what's happening there? Well, that absolute value function is this right here. So we would just replace that. And this is precisely what we did, kind of behind the scenes. So this is a little bit more detailed of what's going on with the calculations we just did for total distance. So this first integral with the negative in front, this was the distance in the negative direction. And the second integral here, this was the distance that we traveled in the positive direction. So you can see, let's just go back really quick. Keep these two integrals in mind. If we go back, distance in the positive direction, well, what did we do? We integrated from 3 to 4 of just our regular velocity function. And that's because from 3 to 4 we found it was positive. And then for the distance in the negative direction, what did we do? Well, we integrated just our regular velocity function from 1 to 3, but then we made this adjustment with this extra negative in front. And that was because our velocity was negative. So we made this adjustment for the fact that we were traveling in the negative direction. So we calculated this integral, and what did we do? We added the results together to get the total distance. And so this is what we're seeing here with these piecewise definitions, is a little bit more of the kind of the theoretical, the subtlety of working with absolute value and piecewise functions in general. All right. So that's a good example to end with. There's quite a bit going on there. And what we're going to look at next time in the next lesson is we're going to start, well, we're actually going to see the definition of these definite integrals. So we've seen a few applications so far. We've seen how we can use definite integrals to calculate distance, displacement, area under the curve, things like that. And what we're going to see next is, well, what actually is the definite integral? So we'll see you there. Bye-bye.